Hey Rustaceans, and welcome back to Rust Run. Today, we are diving into LeetCode problem 88, Merge Sorted Array. Let's start by reading the problem description. You are given two integer arrays, nums1 and nums2, sorted in non-decreasing order, and two integers m and n, representing the number of elements in nums1 and nums2 respectively. We need to merge nums1 and nums2 into a single array sorted in non-decreasing order. The final sorted array should not be returned by the function, but instead be stored inside the array nums1. To accommodate this, nums1 has a length of m plus n, where the first m elements denote the elements that should be merged, and the last n elements are set to 0 and should be ignored. nums2 has a length of n. Pause the video now and take a moment to carefully read the problem description and examples. Make sure you fully understand what the task is before moving on. Alright, let's break this down and make some key observations from the problem statement. Both arrays are sorted. This is crucial. It means we don't need to perform a full sort. We can use a merge-like process. The merge must happen in place in nums1. This is the biggest constraint. We cannot create a new, larger array, sort it, and then copy it back. nums1 has exactly enough space at the end. It's m plus n long, with the last n slots filled with zeros. These zeros are placeholders, effectively telling us, here's your empty space to put elements from nums2. Given these observations, especially the in-place requirement and the empty space at the end of nums1, how do we efficiently merge? A common first instinct is to start comparing from the beginning and insert the smaller element first. But think about what happens if the first element of nums2, which is 1, needs to go into the first position of nums1, which currently holds 4. We'd end up overwriting 4 unless we first shift 4, 5, and 6 one position to the right. If nums2 has many smaller elements, we'd be shifting values over and over again, and that becomes inefficient fast. This leads us to the critical conclusion. We must start merging from the end. Instead of filling nums1 from the front, we start from the very last position at index m plus n minus 1 and work our way backwards. This way, we're always placing values into either an empty slot, one of the zeros at the end, or a spot that already holds its final sorted value. This clever two-pointer approach ensures we never overwrite data we still need. And best of all, it completely avoids those expensive element shifts. In the next few slides, we'll walk through several key iterations of our algorithm step by step. But if you've already grasped the idea and feel confident about the initial setup, feel free to skip ahead to the coding section where we implement the full solution in Rust. Okay, let's take a look at our starting point. We've got nums1 holding our initial three values, 1, 2, 3, followed by three placeholder zeros. We're told that m is 3, which is the count of the actual elements in nums1. Then we have nums2 with its three values, 2, 5, 6. The problem tells us that n is 3, which is the count of elements we need to merge in from this second array. Up top, you see our three main tracking variables. m remaining and n remaining are both set to 3, because that's how many elements we have left to process from each array. And our right index is at 5, pointing to the very last spot in nums1. Alright, before we jump into the action, let's hit the brakes for a second. I want you to seriously pause the video right now. This slide, with its three main variables, is the key to everything we're about to do. Make sure you understand what m remaining and n remaining are counting and where that right index is pointing. Alright, let's begin the merge. We've got m remaining at 3, n remaining at 3, and right idx at 5. We compare the last active element in nums1 which is 3, with the last active element of nums2, which is 6. 3 is less than 6. So 6 is the larger element. We'll take that 6 from nums2 and slide it right into nums1 at our right IDX. After that, our n remaining drops down to 2 because we've just used an element from nums2 and our right IDX also moves back one spot to 4. Moving on to the second iteration. We've got m remaining still at 3, n remaining is now 2, and our right IDX is at 4. We compare the last active element in nums1, which is still 3, with the last active element of nums2, now 5. 3 is less than 5. So 5 is the larger element. We'll take that 5 from nums2 and slide it right into nums1 at our right IDX. After that, our n remaining drops down to 1 because we've just used another element from nums2, and our right IDX also moves back one spot to 3. Moving on to iteration 3. Our variables are now m remaining at 3, n remaining at 1, and right index at 3. We compare nums1's current last active element, which is still 3, with nums2's current last active element, which is 2. 3 is greater than 2 this time. So 3 is the larger element. We'll take that 3 from nums1 and place it right into nums1 at our right index. After that, our m remaining drops down to 2 because we've now processed an element from nums1, and our right index also moves back one spot to 2. And finally, we've reached our last iteration. We've got m remaining at 2, n remaining at 1, and right IDX at 2. We compare the last active element in nums1, which is 2, with the last active element of nums2, which is also 2. They are equal, and our algorithm is designed to take the element from nums2 in this case. So we'll take that 2 from nums2 and slide it right into nums1 at our right IDX. After that, our n remaining drops down to 0 because we've just used the last element from nums2, and our right IDX also moves back one spot to 1. This is our final step. Since n remaining is now 0, our merge is complete, and the two arrays are fully sorted and merged inside nums1. And finally, this is the moment we've been building toward. Let's implement our full solution. First, let's declare our tracking variables. We create a mutable variable called m remaining and set it equal to m converted to usize. We're using usize because that's the standard type for array indexing in Rust, and this variable will track how many elements are left in nums1 to process. Right below that, we do the same thing for nums2. We declare a mutable n remaining variable, setting it to n, also converted to usize. This will track the number of elements we still need to merge from nums2. Next, we create our right IDX variable. We're setting it to m remaining plus n remaining minus 1. This gives us the index of the very last position in nums1, which is exactly where we want to start placing our merged elements. Now we get to the main logic, our while loop. This loop will continue to run as long as n remaining is greater than 0. This is the perfect condition because once we've processed all the elements from nums2, there's no more work to do. Any remaining elements in nums1 are already in their correct sorted positions at the beginning of the array. Now, inside our loop, we're going to type out our if statement. This is where we check which element is larger. We'll compare the element at m remaining minus 1 in nums1 with the element at n remaining minus 1 in nums2. We use -1 because our remaining variables count how many elements are left, and since array indices start from 0, we always need to subtract 1 to get the index of the very last element. So, if the element from nums1 is larger, we're going to do two things. First, we place that larger element from nums1 into our right IDX position. Then, we need to remember to decrement our m, remaining counter, because we've now processed one element from that array. But if that condition is false, we enter our else block. This means we're going to place the element from nums2 into our right IDX position instead. After we do that, we need to remember to decrement our n, remaining counter, because we've now processed one element from nums2. And finally, after we've placed an element, we move our right IDX one position to the left. This happens every time, no matter which branch of the if statement we took, because we are preparing for the next element in the next pass of our loop. Okay, let's submit our code and see what happens. And, oh, it looks like our solution failed. The error log shows an index out of bounds, which is a classic issue in these kinds of problems. So, where did we go wrong? The failure happens when m remaining becomes negative. That's not a valid index, and Rust correctly stopped our program. The fix is simple but critical. We need to add an additional check to make sure the elements in nums1 aren't finished yet. So, we're going to update our if condition. We first check if m remaining is greater than 0, using a logical AND to ensure that if nums1 is exhausted, we don't even try to check its elements. Boom! The code finally compiles and no panics in sight. I'd say that's a pretty awesome reason to celebrate. So go ahead, smash that subscribe button, and join us on the next wild ride in our Rust run.